So here's lesson 2 on rotational dynamics. And just as in the last lesson we saw a correspondence between linear motion and angular motion, there's also many similarities between forces that act in the linear direction and those that act to cause rotations. And so we come to something that we need to define first, which is the moment of inertia. And we say that as it turns out, Newton's laws also apply to rotating objects. They just look a little bit different. And the concept of inertia specifically becomes slightly more involved. Mass, as you will recall, is a measure of an object's inertia. Okay, so if an object has more mass, it becomes much more difficult to accelerate. If it has a little bit of mass, it's easy to accelerate. For an object that's rotating or spinning, mass is an important consideration, but also its distribution about its axis of revolution becomes very, very important. And so let's take a look at the following diagrams. Here's a rod, and it's spinning about its axis. And so its mass is distributed pretty evenly along its axis of rotation. And so each little bit of mass in the rod has a very small radius of rotation. It's not rotating very much. But if we consider another rod that's rotating in a different way, it's rotating about an axis that's through its center, but it's not through it's not along the axis of the rod, it's right through the center of the rod, and the axis of rotation is perpendicular to the rod's length. Each bit of mass in this rod, its mass distribution, has a much farther distance from the axis of rotation. So its mass is distributed at a much larger radius. And these two things really will differentiate how much force it's going to take to either speed one of these up or slow one of these down. And of course the figure on the right hand side produces much more inertia and is much more difficult to get going and is much more difficult to stop. The moment of inertia is the angular equivalent to mass. It depends on the object's mass, as we've seen, but also on the object's rotation axis. So different objects, and we just looked at an example of a rod, but different objects in different shapes spinning along different axes will produce different moments of inertia. And so for a ring of mass, or a hoop, rotating about its central axis, the moment of inertia I is equal to mr squared. And the moment of inertia is measured in kilogram meters squared. Okay. M is the mass of the ring in kilograms, and r is the radius of the ring in meters. And so we've got a chart over the next couple of pages that really just provides the different moments of inertia for different objects. And so here, let's take a look at a couple of them. As we just discussed, the hoop about a central axis, there's a little diagram of it. So that would be spinning about its axis. I is equal to mr squared. If instead we take an axis that is equal to a diameter of a hoop, and now we spin it around that axis in the next one down, I changes to 1/2 mr squared. If we give that hoop a little bit of a thickness, and now we say, okay, now it's a hollow cylinder, and it's going to spin about its axis, we have to change. If that now has a thickness to it, I is equal to 1/2 m r1 squared plus r2 squared. A very, very thin hollow cylinder is just exactly the same as the hoop. A solid cylinder or a disc, so something that's really quite thick and spins, is 1/2 mr squared. And so you can see that there's many different orientations. Here we get into some of the rods. So a thin rod, like one of the earlier examples, it's spinning about an axis that's perpendicular to its length. It has a moment of inertia of 1/12 ml squared, where L is the length. If you take a rod and spin it about the end, it's 1/3 ml squared. Different moment of inertia. The next one down is a solid sphere, and we can spin that sphere around any diameter because the symmetry of a sphere is such that it will always give us the same moment, which is 2/5 mr squared. But now instead of a solid sphere, a thin sphere is a little bit different. It's 2/3 mr squared. And finally, now we have these thin sheets. So they're basically rectangles. Thin sheet with its axis of rotation parallel to one edge, as you can see, but passing through the center of the other. We get 1/12 ml squared. A thin sheet spinning about an axis that is along one edge, 1/3 ml squared. And if we were to turn the thin sheet so it was on its face, with the axis through its center, we'd have 1/12 ma squared plus b squared, where a and b are the dimensions of the sheet. And those are the different moments of inertia.